Okay, so we'll continue where we left off tomorrow. Remember, we not tomorrow, yesterday. Remember, we started with the memory systems part of the lectures yesterday, and today is the second memory systems lecture out of 5 lectures that we will have on memory systems. One could argue that we're not doing justice to memory systems, but that's all we have in a semester, right? We have to build up the background and other things also. That's important. Okay, so I'm going to jog your memory at the beginning of this lecture. We're going to go through some things quickly that we have discussed, and then we're going to go into the design of the memory hierarchy and caches. And that's going to be important because most of our systems today are memory hierarchy and caches, as we discussed yesterday. Right? So remember, there's an extra assignment, Amdahl's law. So you'll have the privilege of reading Amdahl's original paper, which I think people should do, since this is very fundamental. And remember the readings. I'm going to cover a lot from our computing handbook book chapter that talks about memory systems in a very, let's say, basic way, fundamental way. So recall, we talked about memory organization yesterday, and this is the organization that all memories have. I'm going to show you examples from some really old memories that have this 2-dimensional array structure also. I'm not going to go through this again, but you should know how a memory array operates. And memory eventually consists of a hierarchy of arrays, right? Arrays of arrays of arrays of arrays. And we showed that example yesterday from DRAM. And recall, we covered memory technologies. SRAM is a key technology that's used everywhere in our computing systems today. It was developed in 1960s, and it's very successful right now. DRAM, which was also developed in 1960s, is also quite successful today, right? And you know the properties of SRAM versus DRAM, which we covered yesterday, right? Because of the properties of the technology, that determines how we use the different technologies in the system. SRAM is mainly used for caches. DRAM is used for main memory. And one of the main reasons why DRAM is not integrated onto the processor chip is because of this manufacturing part over here, this last one. Manufacturing requires putting capacitor and logic together. And if you want to optimize the manufacturing for capacitor density, increasing the density of very small capacitors so that they can reliably store charge, that's a totally different fabrication process compared to fabricating CMOS transistors. So if you're wondering why we don't have DRAM on our processor chips, that's the reason, basically, because of manufacturing reasons. You could have it, except what you would have if you have a capacitor that's optimized in a chip that's optimized for logic, that capacitor will be very large and very leaky. So it won't be like the DRAM chips that we know. So manufacturing is very important also, as you can see. Okay, we also talked about phase change memory. Clearly, this is, even though it's an old technology, it's new to the main memory domain, let's say, and the storage domain. So because this was used in rewritable CDs, but more recent works showed that you could use it for main memory as well as solid state disks. So this is actually disrupting the memory hierarchy as we know it today, after such a long time, if you will. For a very long time, memory hierarchy was SRAM, DRAM, hard disks, tape. Now SSDs came along, that was disruptive also. And then maybe phase change memory can disrupt the hierarchy again. Right? Okay, we're going to go back even further later. And recall that this was what we discussed, the trade-offs between DRAM and PCM, and the trade-offs are longer, as you can see over here, because there are different things that come into play with phase change memory, like endurance problems. There are no endurance problems in DRAM, but there are endurance problems in PCM, and there's non-volatility. PCM is non-volatile, which enables it to be used potentially as main memory replacement, as well as an SSD replacement. So it could actually serve both parts, if you will. So in that sense, it's actually a nice technology going forward. But as we discussed, it's slower access, even though it's higher density. So this is a very fundamental trade-off, access latency versus density. You cannot get both, let's say, at the same time. And that's going to be why we're going to build a memory hierarchy as well. So I also, at the end, discussed charge versus resistive memories. Existing memories, maybe one of the TAs can admit students or remove the admission online. It's very disruptive. I don't know why Zoom likes me to do it as a presenter, right? Disruptive presenter seems to be the principal Zoom employees. That's probably not a good principle for this. You guys can disrupt me, of course, right? Asking questions, but the software that I'm using to present disrupting me probably is not the best trade-off employed in a software. design. Okay, but anyway, today's memories are charge memories, charge-based, and these emerging resistive memory technologies look very promising because they're much more scalable in terms of density, and also they are non-volatile as well. So there are a bunch of memory technologies that people are investigating right now. You can actually buy chips for a PCM, as we discussed, like Intel has this Optane memory, STT MRAM chips. You can also buy them, put them in your memory slots. These are more emerging, let's say, and they all have different properties, which we're not going to talk about. If you're really interested in this, you can certainly watch online lectures where we talk about different technologies, as you can see, and or attend the computer architecture classes going forward. We cover some of these in the seminars as well. So as we discussed, one of the things emerging technologies can disrupt is really the system level view. So you can have only phase change memory that could be used as both working memory as well as storage. And that changes the whole system design, if you will. Okay, but we don't have time to talk about it. If you're really interested, you can definitely take a look at these lectures. I mentioned flash memory as an emerging memory technology, let's say 30 years ago. Actually, even 20 years ago, flash memory was emerging, let's say, by some definition of emerging. But today, flash memory is everywhere, right? So that's the importance of memory technology. Flash memory, in my opinion, has really revolutionized our lives, the way we interact with computers, the way we carry them around, etc. If it wasn't for flash memory, I don't think we could have things like really smart smartphones today. And this is something that I showed yesterday, but I didn't really talk about. I don't expect you to see everything over here, but this is very interesting. So if you look at flash memory, this is a flash memory board. It gets connected to your processor, let's say motherboard. And if you look at this board, this is a system by itself. It's amazing. For this storage system to work, you need to have some processors. In fact, there are some ARM processors over there, simple processors like we have seen. They actually do a lot of storage management tasks. There's error correcting codes, etc. There's some randomization, encryption, compression, as you can see over here. And this is the host. There's an interface to the host. Host is not shown here. Host is really the host processor, let's say. And you can see that flash memory has its own DRAM so that it can do buffering of the data. So even though these are the flash chips, to control the flash chips, you need an entire system, if you will, and also other memories as well. So you can think of this as a memory hierarchy within a memory hierarchy. Like you have this entire system over here, but to make flash memory operate, you have another memory hierarchy, another system to make it work. And that's what's fascinating, actually. If you really want to know more about this, you can take a look at this paper, which is quite accessible, I think, to a general audience. And we have lectures also. As I mentioned yesterday, memories can be two-dimensional, like planar, like this, but they can also be three-dimensional. In fact, flash memory is already three-dimensional. When you buy SSDs today, there are hundreds, more than 100 layers of flash memory stacked together, and that enables scaling in a much better way. Again, I have to just say this because we don't have time to go into the details of 3D stacking, for example, which is fascinating in terms of fabrication and what it enables. But you can certainly watch the lectures if you're interested. And we actually have a special course on flash memory and SSDs that you can follow if you're interested. Okay, so this is where we ended, actually. I recommended some memory-centric computing systems tutorial and processing in memory tutorials if you're really interested on this topic. I think going forward, maybe if we actually take this class or teach this class 20 years later, we're going to be talking more about memory-centric computers. There would be more processing in the memory side, storage side, and less focus on the processor-centric computing, if you will. If you think about it, existing systems are processor-centric. But think about the future, 20 years, 30 years down the road, will they still be processor-centric? I doubt it because of the huge bottleneck that we're seeing in memory. Okay, so that's kind of an overview of what we discussed, especially toward the end yesterday. So let's talk about the memory hierarchy now. Any questions so far? This is all good, interesting? Yes? So the short answer is probably yes, because its latencies are still long. It just makes some things faster, right? It makes the memory hierarchy a little bit better, let's say, but it will not completely change the bottleneck. Right? That's the problem. I think the main reason for the bottleneck is because we're very processor-centric, right? The data, if you want to process it, we have to bring everything to the processor, and that causes this huge bottleneck, in my opinion. But it will improve the system, of course, right? Compared to it will provide incremental improvements, as we have been doing in real systems. Now, that's not to. That said, I'm not trying to trivialize the improvements, right? Existing improvements are actually quite good. Flash memory, for example, improved our lives a lot. I said revolutionized, but it doesn't completely solve the memory bottleneck, right? It solves part of the bottleneck, but the bottleneck, I think, remains largely. Okay, that's a very good question. Anything else? Okay, let's jump into the memory hierarchy. I'm going to show you similar pictures, but these are actually memory hierarchy pictures, right? You can see that there's a hierarchy of memory, L2 caches, a shared L3 cache, memory controllers, and physical memory, and then storage system that's not shown over here. Inside the cores, there are L1 caches and register files. This is really our memory hierarchy, and existing systems dedicate a lot of resources to the memory hierarchy. You can see that people actually do interesting things like system level caches that are shared by the GPU and CPU, such that they can have their own address space. And you can see that the memory hierarchy is clearly visible over here, right? SRAM, a lot of SRAM is here, and a lot of DRAM backs it up. And most of the system is memory hierarchy. And these are older systems, as you can see. So we're going to cover some of the interesting things in the level 2 cache, for example, soon. We're going to do the hierarchical performance analysis of this system, which is Pentium 4, in a little bit. But basically, I've shown you all of these before, and these basically show that memory hierarchy is the biggest resource today. And as we discussed yesterday, ideally, what we want from memory is zero latency, zero access time. We want the data right away. Infinite capacity. We want to store all possible data that we generate. Zero cost, and infinite bandwidth, so that we can support multiple accesses in parallel. As I said yesterday, you cannot get all of them. So unfortunately, we have to trade off different things so that we get to a nice point in the trade-off space when we design memory. So you can design each individual memory chip so that you get to a nice trade-off. But unfortunately, you cannot get to the ideal, right? Ideal memory's requirements clearly oppose each other. Bigger is slower, as we discussed yesterday. You have long interconnects for sure, regardless of the memory technology. Faster is more expensive, and higher bandwidth is also more expensive. So bigger, it takes longer to determine the location, as we discussed. Everything becomes bigger. Row decoders, column multiplexers, interconnects, array sizes. Faster is more expensive. Again, you can get a faster memory technology. Like going from left to right here, you become slower. But you also, going from right to left, tape to disk to SSD to DRAM to SRAM, you become faster. But you also become much more expensive, basically, because the area of per bit storage increases. With SRAM, we discussed that. And then you can have latches over here, which is much larger, right? And higher bandwidth is more expensive. Basically, you can add more bandwidth by adding more banks, more ports, more channels, higher frequency interconnects, or faster technology. Unfortunately, doing all of those increase your cost, right? Basically, you cannot get bigger, faster, and higher bandwidth at the same time. Even if you ignore higher bandwidth, you cannot get bigger and faster at the same time. And this is actually real data from today that shows that bigger is slower. In 2022, circa 2022 numbers, these are the numbers. I'm not going to go through all of these, but you can see that SRAM is an order of magnitude more expensive than DRAM. PCM is cheaper than DRAM, but slower. Flash memory is even cheaper than PCM, but slower. Hard disk is even cheaper, but slower. You can see that the latencies are over here also. Maybe a better way of, other technologies have their place as well, but we have not put them over here. Now, maybe this is a better way of looking at it, a table version of what I showed you earlier. And these are different technologies, and these are the capacities that you can get them today, and these are the latencies, right? Hard disks are in the order of milliseconds, flash memory is microseconds, PCM, if it's used as memory, is actually on the order of nanoseconds, but still slower than DRAM. And as you go from top to down, latencies increases, capacity increases, and cost reduces. And this actually is what really makes us think about a memory hierarchy clearly, right? So this was the 2011 version, actually. I've been teaching this course for a long time, as you can see. In 2011, we had these numbers. And you can, if you want to compare, it was much more expensive at that time in 2011. And we didn't have some of the other memory technologies that were included earlier. Okay, but ideally, we want both fast and large, right? So the question is, we're not going to get it with a single memory technology. Can we somehow achieve it with multiple levels of memory? And that's the idea of a memory hierarchy. Basically, we want to have multiple levels of storage, progressively bigger and slower as the levels get farther away from the processor. We're still processor-centric thinking, right? But we want to ensure most of the data that the processor needs is kept in the faster levels or faster level, depending, and you can have multiple levels clear. That's the idea, basically. That's the idea of a memory hierarchy. Very simple, if you will. It's not that big, but this is what covers most of our hardware real estate today. So this is one picture of it, basically. You have small and fast caches and large and slow main memory. This is showing only 2 levels. Okay, and you can generalize this clearly. Ideally, you have some fast and small memory, and you have another large but slow memory. And with good locality of reference, which we have discussed before, actually, we're going to discuss more, the memory appears fast and big to the processor. So you get the best characteristics of both while avoiding the small and slow parts of the different levels, if you will. That's the idea. You want to manage this memory hierarchy in some way such that accesses are fast and the memory appears as large. Makes sense, right? By having this hierarchy. Of course, if you don't manage it well, you can get small and slow as well, right? You can get the worst characteristics of the levels. So management of the memory hierarchy will be very important in getting the best characteristics of these different levels in the memory hierarchy. So of course, maybe you're not able to do that with 2 levels. So you start adding more levels, as we will see. And today's hierarchies actually have 5, 6 levels, as we will see. And we normally consider registers as part of the memory hierarchy as well. In fact, if you remember lecture 9, when we introduced the registers as part of the von Neumann model, we said that these are fast temporary storage. And the reason we have them is memory access is too long. So why don't you have a register file that is close to the arithmetic logic unit, such that you can store the temporary variables that you need often or soon, so that you can access them faster. And we call this the locality of reference, right? You need that locality of reference. And we're going to exploit essentially the same thing. So registers are really part of your memory hierarchy, except they're managed in a different way, as we will see. Okay, any questions? Now we're going to build that memory hierarchy. So basically, this is maybe a more realistic version of the memory hierarchy. Today, you have the register file, part of the memory hierarchy, caches, multiple levels of caches, main memory, hard disk. Hard disk is part of the memory hierarchy also, as we will see in the virtual memory lectures, because what you actually, this main memory may not be enough to capture what you're using. And there's some management that happens between hard disk. Hard disk becomes a backup store for main memory. So main memory becomes the cache for the hard disk. It becomes a working memory as well. So the fundamental trade-off is fast memories are small, large memories are slow, basically. So also there are other cost and bandwidth trade-offs as well, right? So as you go from left to right over here in this memory hierarchy, you try to get the best of every single level, if you will. As you go from left to right, latency of the level increases, cost of the level decreases, size of the level increases, and bandwidth of the level also decreases. So here you have very high bandwidth access to the register file, whereas you have very low bandwidth access to the hard disk because it's totally off the chip, if you will, and the access is through some relatively low bandwidth interconnects. Okay, so this is the example from your book chapter that I assigned. And you can see these are some real numbers, realistic numbers. Again, these are realistic for real systems. So hopefully this is clear. So let's talk about why this works. So why this works is very similar to why registers work, right? Registers work because programmer or the compiler exploits locality of reference in the variables that you're using. You want to put the variables that you're going to use often or soon into the register file. And that's because of the principle of locality. If there's no locality in the variables you're using, you're not going to be able to exploit that fast temporary storage very well. But fortunately, programs exhibit this behavior of locality. In fact, this principle, I think, is much more general than just computing. It's a principle of life, potentially. I believe, for example, one's recent past is a very good predictor of their future, near future at least, perhaps. For example, temporal locality. There are 2 types of locality. One is temporal, the other is spatial. So time versus space, again, comes here, right? Some people in quantum physics argue that these are the same thing. Maybe we don't understand the world enough. That's why we're divided into time and space. I'm not sure. But temporal locality says if you just did something, it is very likely that you're going to do the same thing again soon. Like you're sitting here, 1 second later, you're probably going to sit here again, right? So that's basically a very simple temporal locality principle, right? So another example, since you're here today, there's a good chance you will be here again and again regularly, right? That's another temporal locality thing, if you will. Spatial locality is in space, basically. The same principle in space. If you did something, it's very likely that you will do something similar or related in space. I like this analogy. Every time I find you in this room, for whoever comes, you're probably sitting either at the same space or close to the same space. And people are sitting closer, like there are clusters of people who are sitting closer to each other, and this never changes. But there are also some random people that randomly sit at different places. So not everybody obeys this principle, if you will. It's as with every rule or principle, there are exceptions to the principle also, right? But these principles are so dominant in programs that the memory hierarchy works in general. When it doesn't work, it's terrible, actually, because you have to go through all levels of the memory hierarchy, and things become less predictable, right? If I want to find someone, for example, I have to look everywhere, right? That's the random access problem. Okay, so memory locality is very similar. A typical program has a lot of locality in memory references. Typical programs are usually composed of loops, and loops usually have a lot of locality, but this is not the only reason why programs have locality. So for example, temporal locality is a program tends to reference the same memory location over and over and over many times, all within a small window of time. This is why registers work. This is why caches work, basically. So an example is you fetch one variable, and then you want to add that variable to 20 other variables, right? So that variable clearly has a lot of locality over here, okay? Spatial means that a program tends to reference nearby memory locations within a memory region, within a window of time. So we're talking about now space, memory space. You have some memory address and then a region around it, and you tend to reference around that region. And clearly there are reasons for it, and most notable examples are instruction versus data. For example, in instruction memory references, in the von Neumann model, what we do is we sequentially go through the program, right? We always increment the PC program counter by 4 and access memory. Clearly, those are spatially correlated references, right? You're streaming through the memory, sequentially going through memory. So you have a lot of spatial locality in instruction stream references. We talked about in SIMD and GPU lectures, we talked about arrays and vectors. And whenever you remember the example where we actually are adding together two arrays, then you're basically sequentially going through both of the arrays, streaming through both of the arrays. And if the arrays are mapped consecutively, each array is mapped, the different elements in the same array are mapped consecutively in memory, then they're basically spatially correlated with each other. And that's how you would like to map the arrays, as we discussed in the GPU lectures, right? So that your stride is predictable and as close to 1 as possible, if you will. So these are very intuitive examples, right? That show the spatial locality. Now, if you didn't organize your data well, you may not get spatial locality, clearly. Okay, so caches exploit temporal locality as well as spatial locality. Initially, actually, in the 1965 paper, we're going to mention, that's not the earliest cache paper, but they only exploited temporal locality at that time. And then there are other papers that talk about spatial locality. But how do you exploit temporal locality? Since temporal locality means that you're going to access the same memory address again and again, why not store the recently accessed data in some automatically managed fast memory? That's called a cache, basically. I'm going to more formally define a cache later, but cache usually overwhelmingly means today that the storage is automatically managed. That's why we don't think of registers as caches. Registers are more like scratchpad memory, another level of memory, if you will. Okay, so that's the idea, basically. So the anticipation is that same memory location will be accessed again soon because of the temporal locality principle, right? We already said this, basically. And this is what Morris Wilks had in mind in the 1965 paper that is assigned as one of your potential readings. And I'm going to read this basically over here. The use is discussed of a fast core memory. We're going to show a picture of core memory later on, of say 32,000 words as a slave to a slower core memory of say 1 million words, in such a way that in practical cases, the effective access time is nearer that of the fast memory than that of the slow memory. I think this is a beautiful description of a two-level memory hierarchy and a cache, as you can see over here. Okay, so that's temporal locality. So his cache at that time did not exploit spatial locality, but many caches today do exploit spatial locality. Because of the principle of spatial locality, people said, why don't we store data in addresses? So we're accessing one location. We don't store just that location in the cache. We also store surrounding locations, data in locations that are adjacent to the recently accessed in this automatically managed fast memory. Makes sense, right? So basically, you divide the memory into blocks, as we will do. You store a block of data into memory, and where the block is bigger than what you really needed at that point in time. Okay, so you basically carve out a bigger space from the memory hierarchy and put it in your cache, even though you did not, the processor did not request the surrounding ones. You're just anticipating that the processor will request it soon. So basically, you're logically dividing the memory into equal sized blocks. Fetch to cache the accessed block in its entirety, where the block is bigger than the data that's requested by the processor. As I said, anticipation is that these nearby memory locations will be accessed soon. Okay, so in a sense, we're doing some kind of prediction in both, right? Temporal locality says we're going to access this block again, this particular memory location again, and spatial locality says we're going to access. The prediction is that we're going to access the surrounding locations soon. Okay, we already said this. I think there are reasons why this works, and this is what IBM 36085 implemented. This was the first commercial and quite successful processor that implemented a cache. And this beautiful paper describes it. It has a 64 kilobyte cache. It's small, clearly. Although L1 caches did not increase as much because, as we will see either this lecture or the next lecture, probably this lecture, that L1 caches are very tightly integrated into the processor. Their requirements are very tight to the processor because you have to supply the data quickly to the processor, ideally, right? Other caches are more relaxed in terms of how big they can be. And the block size is 64 bytes. Actually, a lot of block sizes are today 64 bytes also. You can see 1960s, 2000, not a lot has changed. Although other hierarchy levels have increased the block size. Okay, if you're interested, this is a very beautiful paper that describes the IBM cache in 1960s. I like this analogy for a memory hierarchy as well, right? You're probably all reading books. Hopefully some computer architecture books also among them. And what you're really currently reading is in your hand. Maybe not right now, but when you're actually reading the book, you're really having the book in your hand and you're exploiting the locality in that book, right? You're not jumping through between different books at the same time. And you have fast access to your hand, clearly, and but you don't have a lot of capacity in your hand, right? At the same time, probably you can carry 2 or 3 books, right? Usually 1, right? If you want to really pay attention, of course. And the books that are recently used, maybe in your desk, right? Or the books that you anticipate to be recently used, recently are going to be in your desk. And the books that are not so recently used, but maybe they're going to be used, are in the bookshelf. And the books that are not recently used, and maybe you don't anticipate them to be used anytime soon, are at boxes at home. And some other books that you're never going to use are probably thrown away or in the storage, right? But you can see that the trade-off also exists over here, right? Until the desk gets full. So there's some capacity limitation. As you go from top to bottom, capacity increases and latency also increases. And data organization also matters, right? You basically exploit temporal locality in managing these, hopefully. And you may want to exploit spatial locality in your bookshelf, for example. If you organize the books that you're going to need around the same time, around the same space in your bookshelf, you can more easily find them and bring them, right? So for example, let's say you have 10 computer architecture books. You put them randomly in your bookshelf. It's going to be tough to find all of them at the same time, right? If you need them around the same time, let's say. But if you organize them well, you put them around the same space, and you can get books consecutively from your bookshelf, put it on your desk. That's the spatial locality principle, right? Spatial locality works if your data is organized nicely and you're touching the space, a region of memory around the same time. Okay, I like this analogy because I think it shows both temporal and spatial locality as well as the trade-offs in the memory hierarchy. Of course, we can go deeper and deeper and analyze this bookshelf, but that gets boring after some time. Okay, so let's talk about caching in a pipeline design. So I already mentioned this. The cache, especially the L1 cache, needs to be tightly integrated into the pipeline. Ideally, remember when we were designing the pipeline, we actually had magic memory. We said in one cycle, we get the data. If we don't get in one cycle, we stall the processor. Okay, in an out-of-order processor, you can tolerate some latencies, but if your latencies become larger, the latency tolerance becomes harder also in an out-of-order processor. So ideally, your level 1 cache should supply the data as quickly as possible, ideally in one cycle, so that load-dependent operations do not stall. So if you have a high-frequency pipeline, you cannot. This means that you cannot make the cache large, because if your frequency is large, you need to get the data in one cycle. Your cache cannot be very large, otherwise it will take too long to access, right? But we want a large cache and a pipeline design ideally. So how do you get that? Well, that's why we have cache hierarchies today. It's not just one level of cache. It's actually one level plus many levels, and then the main memory. So level 2 cache is introduced because of that reason, right? Okay, so of course, now the trade-offs are kind of interesting, right? Level 1 cache is very tightly integrated into the pipeline. So its trade-offs are very tight to the pipeline, meaning the frequency of the pipeline determines the size of this also. And also the latency tolerance mechanisms that you have in the CPU determines the size of the L1 cache. L2 cache is a little bit more relaxed. It's less dependent on the decisions that are made in the CPU, because L1 cache hopefully is supplying the data quickly to the CPU. L2 cache's job is hopefully not going to the memory that much, right? And then, but that's, again, it becomes a trade-off, because sometimes L1 cache doesn't work very well, and you don't want to spend a lot of time going into the L2 cache, so you cannot make L2 cache very large as well. So that's why people introduce an L3 cache over here. So as you go from far away from the CPU, you become less coupled to the CPU, basically. Okay, think about this. This is all processor-centric, though. If you actually do processing inside the memory, as like we envision, things may change. So it can be extremely disruptive. Okay, so let's talk about manual versus automatic management, because we kind of discussed this, but I think it's so important to discuss this as well. So manual means programmer manages the data movement across levels. It could be the compiler also, clearly. It could be the system. Well, it's not the system. Let's not say programmer, compiler. Automatic means hardware manages data movement across levels transparently to the programmer, with some system support potentially in virtual memory, as we will see. So manual is clearly too painful for programmers on substantial programs. This is how register files are managed, right? Compilers or programmers manage it. And in the past, I will show you pictures of this core versus drum memory. In the 1950s, programmers used to manage main memory, physical memory and storage, and it was a pain, actually, a lot of pain. That's why people developed the virtual memory subsystem. But it's still done in some embedded process where programmer knows a lot about the program and things are more or less predictable. Access patterns are more or less predictable. For example, many embedded processors have on-chip scratchpad SRAM. Normally, we don't call manual managed memory as cache. It's called scratchpad or another level of memory, because that address space is visible to the programmer, right? It's not automatically managed. So automatic management is synergistic with the name cache. So if it's manual management, it's called the scratchpad. So embedded processors have it. GPUs have it, actually. I will show you. You actually discussed this in the GPU lectures, but GPUs have a part of memory that can be used as a scratchpad by the programmer, because the programmer may know exactly how the programs behave, and they want to actually allocate fast memory to some parts of the to the parts of the data structures that they are going to be that they expect are going to be touched often, for example, right? Now, unfortunately, GPUs have a bad name for it. At least one company has a bad name for it. It's called shared memory. It's a terrible name for a scratchpad memory, because shared memory normally means that it's shared by multiple different processes, etc. Anyway, people don't name things nicely, but if you hear shared memory in GPUs, it's really scratchpad memory based. It could be something else also, unfortunately, because it's called shared memory. Right? Okay, machine learning accelerators also have a lot of scratchpad memory, because a lot of the accesses are quite predictable in neural network computation, for example. So a programmer or the compiler can nicely manage this memory. But the key is basically you have a different address space over here that you can allocate into. Automatic is completely different. We do things transparently to the programmer. So as a result, programmer's life is easier. Programmer doesn't need to do anything, basically. And magically, programs become faster because somebody, hardware, keeps the data in an internal cache that's not visible to the programmer. This sounds nice, right? So as a result, the average programmer doesn't need to know about caches. You don't need to know how big your cache is, how it's structured, etc., to write a correct program. But if you really want to write a fast program, then you may need to know a little bit about your caches so that you can restructure your access patterns in your program. We're going to talk about that in the next lecture a little bit. But at the software level, you can do a lot of optimization to restructure your access patterns such that you can take advantage of these different memory hierarchy levels. Okay, so this is actually an example of the, programmer microarchitect trade-offs, right? Here, the programmer's life is hard, microarchitects is easy. Here, the programmer's life is easy, microarchitect's life is hard. But if you really want to get the maximum performance out of a system, as a programmer, you cannot avoid some amount of manual, at least rewriting your program so that it can fit the memory hierarchy levels. Okay, so let's take a look at a modern GPU. A modern GPU is actually quite interesting. It didn't used to have caches initially. Automatic management was not there. But more recent GPUs, this NVIDIA Ampere that you have seen actually earlier, I think, in Juan's lecture, you can see that there's an L1 cache that can also be used as a scratchpad. And it's 192 kilobytes per the streaming multiprocessor. So basically, there's an option for the programmer. You use it as a cache and don't worry about the management of it, or use it as a scratchpad, right? L2 caches automatically managed. Going forward, maybe we'll see how things evolve. And these sizes are increasing. This is more recent, as you can see. These two slides are the same, except their pictures are different. But basically, cores have increased, but cache sizes have also increased. They can still be, L1 cache can still be used as a scratchpad or an automatically managed cache, and L2 cache sizes are increasing as well. And if you look at the wafer scale engine, so that was a GPU. You can actually program these. You can find out how to do that if you're interested. This is the machine learning accelerator by Cerebras that we have studied, at least superficially. If you attended the earlier lecture, you studied it a little bit more. You can see that it has on-chip memory, right? Let's take a look at what that on-chip memory is. 18 gigabytes, that's a lot. Basically, this huge huge wafer is divided into 84 dies. Each die has 4,500 tiles or so. Each tile looks like this. It's very regular, basically. Each tile has some machine learning accelerators, some connectivity, interconnection, and there's some SRAM memory. And this SRAM memory is scratchpad, basically. The programmer or the compiler figures out what to put over here based on the computation that's happening over here, right? And you can see the properties over here. It's only 48 kilobytes in each tile, but if you multiply it by the number of tiles and the number of dies, you get to 18 gigabytes in the entire chip. So it's very distributed and parallelized, as you can see. So in this particular case, there's no, here shared memory is used in the right way. Shared memory, memory that's shared across tiles, basically. You have to move data from one tile to another, as discussed in the earlier seminar that you may have attended. Okay, and this memory is increasing also, as you can see. So these are examples of scratchpad memory that exist in real systems. When you know how to partition your data, how to move your data into fast memory, it's a good idea for the programmer or the compiler to do that. Now, let me give you a historical perspective. These are actually memories of 1950s and 1960s. So when people talk about drum memories, these are magnetic memories. These are completely replaced today by SRAM and DRAM. So that's how the technology have changed. So these are drum memories, you can see, and this is the core memory. I'm not going to go into the principles of this, but basically it's magnets. And you can see the magnets over here, but you can see the two-dimensional array structure, right? So that's very fundamental. Even the magnets are placed in a two-dimensional array structure, and you can see the word lines and bit lines over here. Interesting. We don't need to know more about that in terms of magnetic memory. But I think it's instructive to look at these pictures because these memories don't exist anymore. Why? Because they were replaced. And there's a good writing over here. You cannot read it probably, but the cost was one of the reasons, and also manufacturing was another of the reasons. So it was very difficult to manufacture these, and their costs were not as good. And when SRAM and DRAM were introduced, these are the semiconductor memories, clearly in the late 1960s, they basically started to erode the market for core memory. So core memory replaced DRAM memory, and then SRAM and DRAM replaced core memory completely. And you can see that the first successful dynamic random access memory, the Intel 1103, followed in 1970. And its availability in quantity at 1 cent per bit marked the beginning of the end for core memory. Compare that 1 cent per bit to, I don't know, less than $1, a lot less than $1 per gigabyte, per megabyte today in earlier slides. Okay, so that's what Maurice Wilks talks about in this paper. You can see that it talks about fast core memory. He basically refers to this core memory over here. That's why it's called fast core memory, right? He could have said fast memory, right? But people used core memory at that time. Okay, so basically caches are almost always automatically managed today. So when you hear a cache, you should assume automatic management. So you can see over here, by slave memory, I mean one which automatically accumulates to itself words. And maybe we'll read it, that come from a slower main memory and keeps them available for subsequent use without it being necessary for the penalty of the main memory access to be incurred again. So beautiful writing. So let me give you another historical aside. This was not the first cache paper. Actually, there are other cache papers that are quite interesting. This is related to the virtual memory system, but the second one over here essentially depicts a picture that we're going to look at soon. They called it a leukocyte buffer, but basically this is a cache. It has a data storage. This stores the data that's recently accessed, and has some associative address storage, which we're going to call tag storage. And these are the valid usage indicators, meaning whether it's used or not, some frequency of access, let's say. But basically, this is the cache of 1960s. And we're going to see a very similar structure very soon. We're going to call this a data store. We're going to call this a tag store, or metadata store, if you will. And the modern memory hierarchy today actually has many, many levels, as you can see. So it's automatically managed, most of it. There's a manually managed part in the register file, and there's another automatically managed, but not programmer managed, not hardware managed part necessarily, which is the virtual memory part. So if your main memory size is not enough, which is definitely not enough in today's data sizes, even if your memory is terabytes and terabytes, it's still not enough because you need a lot more storage of data. You basically go to a swap disk, which could be part of your main memory, or it could be part of the SSD, for example, or disk, hard disk, or tape. So, and that's automatically managed, and we're going to talk about that. And one thing that's happening today, interestingly, in data centers is, so you think of this as a single node, right? Single processor, a single system. It has this memory hierarchy inside it, including the SSD. But that memory is not becoming enough in some data centers. What people are doing is they have separate storage nodes or memory nodes. This is called disaggregated memory. And across the network, you go to some other node that houses a bigger part of your memory, even a bigger portion of memory. So there's another level of hierarchy somewhere over here, maybe far memory, let's say, in some other node, in some other computer, somewhere else that you can use as your bigger backup, if you will. So this is today, if you're really interested in knowing about it, it's called disaggregated memory or disaggregated storage, where people decouple part of the storage to some other part of the data center, let's say. And this is enabled by very fast interconnects. Of course, they're not as fast as interconnects that we have on a single system, but the relatively fast interconnects compared to what we used to be able to build across, let's say, this room or multiple rooms, or across the Atlantic or Pacific, wherever. Pacific is hard. Atlantic is easier. Yeah, across oceans, basically. So we're able to build much faster interconnects today. That's why we're actually, we can offload some of the memory to the other nodes. So I'm giving you this because this is really an extension of the memory hierarchy to another computer that has some more memory, right? And that computer can be designed to have lots more memory, actually. But these may be called memory servers or storage servers, actually. Okay, so let's do some hierarchical latency analysis before we take a break, before we start caches, let's say. So it's important to do this analysis because this is kind of instructive, although it doesn't give you the full picture because it's only about latency, right? Latency is not the only story. You know by now that performance, execution time is the whole story. But latency is still interesting to analyze. So a given memory hierarchy level I has an intrinsic access time, Ti, based on the size of it and based on the technology. So if you want to access that hierarchy level, it takes Ti time. But it also has some perceived access time, large Ti, that is longer than the small Ti. Why? Because you don't always hit in that level, right? Sometimes you miss whenever you access that level. So except for the outermost hierarchy level, there should be a level. I guess I'm going to fix it because otherwise I may forget it. And it may also help you. I cannot write. Okay. So except for the outermost hierarchy level, when looking for a given address at one level, there's a chance that you're going to hit. And the access time is going to be only Ti, small Ti, the intrinsic access time. You're going to get the data from that level. And this is the hit rate, Hi. And there's a chance that you're going to miss in that level, meaning you're not going to find the data in that level, so you have to look at the next level. And the access time is going to be small Ti plus large Ti plus 1, because you're going to access the next level, right? You need to search the next level to find the data. And at a given level, hit rate plus the miss rate should be 1, clearly, right? 100% of the access should be covered. So there's some probability that you will miss, there's some probability that you will hit. As a result, this hierarchical latency equation looks like this. While you're reading the equation, I'm going to hide this. Basically, the access time, the perceived access time of this level is hit rate of the level times the intrinsic access time of the level. You're going to get the data, plus the miss rate of the level times the intrinsic access time of the level to determine that it's going to be a miss, plus the perceived access time of the next level, because you're going to query the next level. Right? And then you can actually, based on this equation, you can simplify this hierarchical perceived access time equation. Large TI equals to small TI plus miss rate from that level times the perceived access time of the next level, basically. Hopefully this is kind of obvious, right? Now you can apply this hierarchically to different levels. So clearly HI and MI are defined to be the hit rate and miss rate of only the references that missed at the previous level, right? Okay. Okay, so you can think about this a little bit. Let's take a look at what this means, basically. If the goal is to achieve a desired perceived latency within some allowed cost, ideally, you would like to make the perceived access latency of the first level, especially, equal to the intrinsic access latency of that level. That means that sometimes you're going to miss, but those misses are not going to be changing your overall latency that much, right? Hopefully. But of course, it's not always perfect. So if you want to achieve this, you ideally want to make the miss rate as low as possible, or keep the miss latency or the perceived access time of the next level. You can also call this the miss latency of this level, right? As low as possible, right? And then there's a trade-off potentially, right? You can trade off more miss rate and the miss latency potentially. Okay, so how do you reduce the miss rate? Basically, you can increase the capacity of this level, but this may increase the intrinsic access latency. So there are trade-offs, basically. You may want to reduce MI, but that increases your intrinsic access latency because you're increasing the capacity at this level, right? Unfortunate. You can lower the miss rate by doing smarter cache management, better cache replacement. You anticipate what you don't need and kick them out, for example, and basically keeping cache as much as possible things that you really need, or do better prefetching, as we will discuss. Okay. So we're going to talk about better cache management because that's going to be important. If you want to keep the perceived access time of the next level low, you want faster outer hierarchy levels. This can help, but unfortunately, this can increase cost, clearly. As a result, people introduce intermediate hierarchy levels as a compromise, right? That's one of the reasons why people introduce intermediate hierarchy levels, so that they can keep the perceived access time of the next level low. So let's do this analysis with Pentium 4. So this is Intel Pentium 4. You've seen a picture of this at some point. This is the 90 nanometer version. And you can see that it has an L2 cache, 1 megabyte, and it has an L1 data cache, 16 kilobyte 8-way. And this is the real picture that you have seen multiple times by now. Now let's do the hierarchical latency analysis so that we can see what's happening here. So this processor was actually quite fast in terms of clock cycle time, 3.6 gigahertz frequency. L1 data cache was 16 kilobytes. Ignore the floating point numbers because floating point requires larger data accesses. Integer requires smaller data access, but even the integer access was 4 cycles. So intrinsic access time of level 1 was 4 cycles, not 1 cycle, right? Because there's out of order execution that's employed, they can tolerate some of the latency of multiple cycles. L2 data cache, they decided to make it 1 megabytes, and it says 18 cycles access latency for integers. Main memory, we're going to assume it's 50 nanoseconds or 180 cycles, but even this is optimistic, let's say. That's the average access latency. So notice that best case latency is not 1. It's best case possible latency could be 4 over here. You always sit in the L1 cache, you never miss. Meaning miss rate is 0 over here. So large TI is equal to intrinsic TI, which is 4, right? But the worst case access latencies are into 500 plus cycles. It could be 1,000 cycles actually. So let's take a look at this hierarchical latency analysis. If miss rate from the first level is 10% and the second level is 10%, which is not bad actually, 90% of access hit in both levels. Now, if you do the hierarchical latency analysis, you start with the T2, you compute this one first because it's hierarchical, right? Recursive, if you will. So how do you compute T2? T2 is equal to small T2, which is 18, plus miss rate from T2, 10%, times TI plus 1, meaning T3, And we're assuming main memory, everything hits in main memory. That's another assumption, right? So basically it's 18 plus 18. 18 plus 180 times 10%. That's 36. Now you plug this into the large T1's equation. So large T1 equals small T1, which is 4, plus 10% times 36. That's 4 plus 3.6, so 7.6. So even with 90% hit rate on both levels, you get 7.6 cycles, which is not close to 4 cycles, as you can see. It's almost double, actually. So let's take a look at another example. If miss rates on both levels are 99%, I'm not going to go through all the calculations. You will see that T1 is equal to 4.2, which is closer to 4 now. But you need to have hit rates of 99%. I said miss rates, but miss rates are 1% only, as you can see. So that's not bad. If miss rate from the first level is 5%, from the second level is 1%, T1 becomes about 5. Okay, maybe it's tolerable without over execution. Who knows? It's close enough to perhaps 4. And if miss rate from the first level is 1%, from the second level is 50%, you still get close to 5. So this is interesting to see, right? Why? Because the second level is not seeing a lot of accesses here, right? Even though its miss rate is very high, a lot of the accesses are hitting in first level. You're not accessing the second level as much. So this also points to different trade-offs in design now. Where do you put your effort? Do you try to optimize the L1 cache? Do you try to optimize the L2 cache? What do you try to optimize the main memory? What do you try to do if your goal is to make this perceived access time at the L1 level equal to the close enough to the intrinsic access time of the L1 level? So that's the richness of the memory hierarchy design, basically. Even with a given memory hierarchy that someone else gave you, you can try to optimize it in many different ways. And the design space is extremely rich. As a result, people have been actually working on this hierarchy for decades and decades. Okay, so this is a great place to take a break. We'll come back 2 minutes after the thing rings, and we're going to talk about caches. So now we're going to cover cache basics and operation. Any questions before we move on? Memory hierarchy usually opens up a lot of questions, but okay, we'll cover some of those questions that may be in your mind that you're not asking. Okay, so let's talk about caching. I mean, clearly we've defined caching, but let's formalize it a bit. But cache is actually a very general concept, right? It's any structure that memoizes or remembers used or produced data, right? And this could be a hardware structure. This could be a software structure also. It could be my bookshelf also, as we discussed, right? But in computing, caching is heavily used at essentially software as well as hardware levels, right? So the goal is to avoid repeating long latency operations required to reproduce or refetch the data from the scratch. Right? That's the idea, basically. You have some long latency operation. You don't want to repeat it. You just put it in your cache and hope that you're going to access it needed again. And a web cache, for example, operates this way, right? For example, my browser has a cache that caches the pages that I recently accessed. And if I access them again, it quickly loads them. Right? That's an example of a software cache that gets employed in many software systems. Operating systems can have a similar cache that cache programs, etc. They may even become more aggressive, right? A browser can be more aggressive. Whenever you visit a page, it can actually preload the cache by checking the links and basically predicting this person is going to access this link. Let me preload it, for example, right? That's an example of prefetching, right? It could be quite aggressive. Some operating systems do this sort of prefetching, for example. They anticipate what the user will load or what program the user will need at what time, and they preload that program into the physical memory from the hard disk, right? If you're more aggressive, you can start the program also, right? That's quite aggressive, of course, as an operating system. So these are examples of caching and prefetching, which are quite interesting, I think, in software systems. In distributed systems, there's a lot of caching that's employed. So the concept of caching is actually all over our systems because there are latencies that are long in our systems. You don't want to refetch the web page again and again and again from somewhere far away. It will take long, basically. So that's the idea, basically. In the processor context, which we're going to talk about, it's most commonly an automatically managed memory structure that keeps recently or frequently accessed data. Basically, the idea is to, a very specific example is to memorize in fast SRAM memory the most frequently or recently accessed DRAM memory locations to avoid repeatedly paying for the DRAM access latency. Right? You can change SRAM, DRAM to other memory technologies clearly, and it will still be a cache. Right? So that's the idea basically. The question is, how do we design it in hardware? So in software, you have a lot more flexibility, right? For example, you may decide to cache 1 page, 1,000 pages, 1 million pages potentially, right? Depending on the space. But the size, the granularity of your caching can be quite flexible in software. Whereas in hardware, you're designing hardware structures. So it's not going to be easy to have cache blocks that are of variable size. That's going to be one of the limitations. You need to more easily calculate where you place a block in memory. So we're going to deal with issues like that now. But at the high level, this is the conceptual picture of a cache basically. It has a limited number of blocks that you can place data into, and each block contains some information, data and metadata basically. Metadata is sometimes called a tag store, if you will. And the data in this case is 64-byte blocks, for example, from physical memory. You cache 64-byte data blocks. Metadata specifies information about the block, for example, the address of the block or part of the address of the block. It can also specify, there should be other metadata that specifies whether the block is valid, meaning whether the data that you have in this particular place is actually something that you should trust. Because when you initialize the cache, there's nothing in there, right? Everything is invalid. So you should distinguish between valid and invalid. It could be some other information about the block, like how frequently it's accessed, like frequency of access, basically, to decide which block to keep in the cache, for example, or which block to kick out from the cache when the cache becomes full and you need something else to bring into the cache. So this metadata can be a lot of things. And we will see some example metadata soon. But this is the high-level conceptual picture of a cache. Then the question is, how do you, one important question is actually, how do you decide what you can place into each cache block? And that brings us to the more logical organization of a cache. Right? The key question is, how do you map chunks of the main memory address space to blocks in the cache? So if you think about main memory address space in terms of chunks, so this is an example with 8 GB address space, you divide into chunks of 64 bytes. These are essentially cache block size chunks. And the question is, where in the physical cache space can this chunk go to, essentially map to, right? Or which location in cache can a given main memory chunk be placed in? And there's a question mark over here. And we will see examples that are very flexible. This chunk can be placed in any potential location in the cache, and that are very not inflexible. This chunk can be placed in only one possible location in the cache. And this will lead to some hardware trade-offs as well as performance trade-offs. And we will see the reason for this. And this is actually the example, several examples we will cover in a little bit more detail. But at the high level, if a chunk, this is assume that you have a cache with 4 possible blocks. You can only have 4 blocks in your cache. A chunk in main memory, any chunk in main memory can map to any possible cache block. This is called fully associative. This is the most flexible organization, basically. At the other extreme, you have this direct map cache. A given chunk can be placed in only one possible cache block. And where it can be placed depends on the address of the chunk. Some bits in the address determine where it can be placed. Why could this be useful? Because it's simple, right? You look at 1 bit, or in this particular case, you need to look at 2 bits because there are 4 possible places, 4 possible cache blocks, as you can see. You look at 2 bits in your address, and they tell you which cache block you can go into. Later, we'll name it a set, which cache set you can place this chunk into. So clear, this is easy. This is harder because you need to search the chunk across all of those blocks. You cannot just look at a couple of bits, and that determines whether the cache has it. Okay, or which cache block this particular chunk can map to. It may or may not be there still, right? That's another question that we will ask. But here, you don't even know which block you are mapped to unless you search all of them. So that's the fundamental distinction between fully associative and direct map, 2 opposite ends of the spectrum. Direct map is simple, but it's not flexible. Fully associative is complex, but it's very flexible. Okay. And this leads to an interesting hardware trade-off as we will see. And in the middle somewhere, there are set associative caches where a chunk from main memory can go to a set of cache blocks, but not to the other set. So in this particular case, we have two different sets. As you can see, each set has two possible cache blocks. This chunk, a given main memory chunk, can go to either to any location, any of the two blocks in the same set. This is called a two-way set associative cache. It's somewhere in the middle, as you can see. Within the set, you need to search multiple different addresses search the given chunk address across multiple different cache blocks. But across sets, you don't need to search, clearly, because which set a chunk gets mapped to gets determined based on a bit, again, in the address. In this case, 1 bit, because you have two sets, as you can see. Generalizing the set associative nature, a direct map cache is one-way set associative, if you will. Basically, a set contains only one cache block. That's what that means. Here, the set contains two cache blocks. A fully associative cache in this particular case is four-way set associative because there are only 4 cache blocks in the cache. Okay, so we're going to see this more. But this leads to a lot of hardware trade-offs. So let's talk about the basics. Any questions on this? I haven't given you exactly how we index this, but we're going to go into the hardware level soon. Okay, so let me give you some terminology. So block, we've kind of been using it, but to define it, it's really the unit of storage in the cache. This is sometimes called a line. IBM terminology actually uses line a lot. In existing terminology, people use both. I like block. So memory is logically divided into blocks that map to potential locations in the cache. I called this chunks earlier to distinguish between blocks, but essentially in the cache terminology, it's blocks. You chunk memory into blocks, and then each block can map to potential locations in the cache. On a reference, whenever you access an address, you check whether the block exists in the cache. It's called a hit if the block is in the cache, and then you use the cache data instead of accessing memory or accessing the next level. Hopefully this is obvious. It's called a miss if it's not in the cache, and you bring the block into the cache if that's the case. Here you have a choice also, right? Maybe you don't want to bring the block into the cache, right? I'm going to give you a very basic cache where we bring every block that we access into the cache. But you can start thinking critically and question, if I know that I'm not going to access the block again, why do I bring it into the cache, right? And that's a great question, actually. Yes, you should not bring it into the cache if you have an idea that you're not going to access it again. This requires a prediction mechanism, though, right? You need to somehow predict either as a programmer or as if you can manage the cache, of course, as a programmer, or at the hardware level, you predict whether the block is going to be needed. Okay, but this is the hit and miss and what you do on a hit and miss. And then there are many other questions. Okay, if you miss, okay, of course, you may have to evict some other block because you missed in the cache is full. How are you going to bring the new block into the cache? You need to evict something else, right? Okay, so some important cache design decisions. We're going to cover some of them, and there are many. Placement is where and how to place or find a block in the cache. This is related to what we already discussed in the earlier slide in fully associative, set associative, etc. We're going to look at that a lot. Replacement refers to what data or what block to remove from the cache to make room in the cache for an incoming data. Granularity of management, we have large blocks, 8 bytes, small blocks, 64 bytes or 256 bytes or 4 kilobytes. Hopefully not 1 megabyte in the hardware cache, that's a lot, but you can think about it that way also, right? Do you do sub-blocking? Sometimes can you bring smaller piece of blocks? We're going to talk about that probably in the next lecture, not today. There's also the variable granularity. Can you imagine variable granularity? That becomes harder now, right? Usually it's a fixed granularity management. You define the block size, and every block size is the same in hardware cache because that makes things simple in hardware, right? Variable granularity, people have explored in hardware, and it's not very easy to design hardware that way. Hardware is nice if things are a power of 2, because you can take the address bits and you don't need to do any calculation on the address bits. And also it's regular, right? Think about that way. Write policy, we're going to talk about that. What do you do about writes? So you may be writing to memory or reading from memory. When you write to memory, what do? Do you actually bring the block into the cache, or do you write directly into the memory? Or do you do something else? Instructions versus data, do you treat them separately or similarly? These are actually two different things clearly, right? And we will see that. Instructions are needed at the fetch state of the pipeline. That's why we have an instruction cache, normally. Data is needed in some other part of the pipeline. That's why we have a separate data cache. That's why these things are separate. First level caches are almost always separate. You don't combine them. But the next level, what do? Do you bring them? Do you have a level that caches both of them? Or do you still separate the L2 level instruction and data caches? Usually they're together. But they have different kinds of locality also. Instructions are usually quite streaming, right? And as we discussed yesterday, the size of the instruction working set is actually much smaller than the data working set in general. Of course, that's not true for every single program, but in general, right? As a result, they have different properties. Do you manage a single cache that consists of both instructions and data? So these are all interesting questions, and we're going to tackle some of them, but there may be other questions also, of course. Actually, there are many, many other questions, but we're not going to tackle. One question is basically, how do you decide whether or not to bring something into the cache, write something into the cache? Okay, so let's talk about how do you design the hardware for this cache. And this is still an abstraction, but we're getting closer to the hardware. Basically, you have an address that you want to find in the cache. And we have two stores in the cache, tag store, data store. And tag store contains the metadata corresponding to each of the memory blocks over here. Basically, data store stores the memory blocks that are cached, and tag store stores the metadata or bookkeeping information that's needed for each memory block. So it could be tag store responds to queries like this. Is the address in the cache? If I want to kick out some block from the cache, which one should I kick out? So it basically stores some bookkeeping information in terms of which memory block is recently used or frequently used, etc. There are different ways of handling it, as we see. But basically, you query the tag store with an address and get a hit or miss signal based on that. If you get a hit signal, then you take the data out of the data store. You may query them concurrently at the same time, tag store and data store, so that whenever you get the hit signal, you also get the data signal or data bits out of the data store. That's what's done in L1 caches. You normally query the tag store and data store concurrently, so that if you hit in the cache, the data is ready for you to take and move on. If you get a miss in the cache, you will get something out of the data store, but it's wrong, meaning that's not something you want because the tag store said what you're looking for is not in the cache, right? If you do concurrent querying of tag store and data store, when you get a miss, you would have access to data store in a useless way, but that's the price to pay, perhaps, right? If you want to get the data quickly in case of a hit. Okay, so we're going to look at both of these. So before we look into it, let's go back to this latency equation earlier. This is a version of the latency equation, if you will. So you can define the cache hit rate as the number of hits divided by number of accesses to the cache, which is hits plus misses essentially. And average memory access time can be defined as hit rate times hit latency plus miss rate times miss latency. Okay, there's some hit latency whenever you get the data that you need. And miss rate time miss latency is whenever you get the data after you miss in the cache, which is hierarchical latency equation, as you can see, because this miss latency depends on what happens in other caches, other levels. So there's one question that I will quickly ask and answer is reducing average memory access time always beneficial for performance? And I think by now you should probably know that the answer is no, because latency is not the only thing that you're optimizing for. Latency is just access latency as part of the performance equation, but we saw latency tolerance, right? You may actually tolerate the latency of some operations without over execution, for example. What we really look for is high performance. So latency is interesting, but what it ignores is the parallelism in the memory system. Meaning there could be other operations going on that hide this latency. So you have this access, for example, that takes, I don't know, 100 cycles. But you have another access that takes 500 cycles. They're both concurrent. It doesn't matter if this access takes 100 cycles or 105 cycles. You're bottlenecked by the 500 cycle access that's going concurrent. Right? That's the idea. So reducing the latency of, let's say, non-bottlenecking operations will not help you that much. We're going to revisit that later on in next week's lecture, basically. But this is an important realization. Even though latency is good to optimize for, this average memory access time is good to optimize for, it's not necessarily going to improve your performance. In fact, sometimes you may increase your average latency and that may improve your performance. We will see that. It may sound counterintuitive right now, but you will see examples of it. So let's start with a basic hardware cache design. So, and we'll examine later a multitude of ideas to make it higher performance. And I already said this basically. Main memory is logically divided into fixed size chunks. That's what we're going to assume. These are called blocks. And cache can keep only a limited number of blocks. And this is the picture that we looked at earlier, right? And the question is basically, how do you do the mapping between a main memory chunk to a potential cache location? And essentially, you take the block address and map it to a potential location in the cache. And the mapping function is really a function of the index bits in the address. So you take some bits, and those form your index, and that index is used to index the tag and data stores. Okay, so this is one function. We're going to show this toy example of a memory. Basically, you basically have an 8-bit address. This is toy, as you can see. Ignore the byte and block. Basically, this is each cache block is 8 bytes in this particular case. So within a cache block, we have some address, but once you get the cache block, you can figure that out using a muxing multiplexer mechanism. But in this particular case, we have 3 index bits, which means that there are 8 possible locations in the cache, and then 2 tag bits. So we'll see. So cache access, how do you do the cache access? You basically have some index bits, part of your address, and index into the tag and data stores with those bits in the address. And the tag store gives you the bookkeeping information related to the data that you're looking for, address you're looking for. You first set the valid bit. Valid bit says whether there's a block there that you placed. If it's invalid, then it's a miss, ignore. If it's valid, then you check the tag bits. There's a block in the cache, but is this the block that I'm looking for? That will be determined by whether the tag bits of the address you're looking for matches the tag bit that's stored in the tag store. Right? If they match, that means that the index matches because you've indexed into the cache, and the tag matches, that means that the block, and it's valid, that means that the block you're looking for is in the cache, and that's it. Okay, that's the idea. So this is the 3 steps of cache access, if you will. And this is what I just said, basically. If the stored tag is valid and matches the tag of the block, then the block is in the cache. That's a cache set. So let's take a look at an example. We'll examine a direct map cache first. Simple, basically, this one, where one chunk will map to only one possible location in the cache. And direct map means a given main memory block can be placed in only one possible location in the cache. I already said this, but it's good to repeat it again. And we're going to see this toy example for which I showed you an address, actually. We're going to look at a 256 byte memory just so that I can fit everything in one slide. The addresses don't become huge, right? 256 byte memory, 64 byte cache, and 8 byte blocks. So let's take a look at placement and access. So if you have 256 byte memory, 8 byte blocks, you have 32 blocks in your main memory. And your main memory looks like this. So this is your entire main memory. And I show you just the block addresses, basically. And I kind of show the index bits and the tag bits. So you have 32 blocks. You assume a cache of 64 bytes and 8 blocks. Direct map means a block can go to only one location. 8 blocks means that because a block can go to only one location, you have an index bits of 3 bits, right? Because there are 8 possible locations, and index bits determine which location a particular memory chunk or memory block can go into. So basically, you have 8 blocks, 8 entries in your tag store, 8 entries in your data store, and assume that you have a valid bit and a tag bits in the data store. And this is how your address looks like. Ignore the byte and block, as I said. It's part of your data store. We're assuming 8 byte blocks. So eventually, you may need one of the bytes only, but you can multiplex them out of the data store. Index is 3 bits because you have 8 possible locations that a given address can map to. But once you know the address, it maps to only one possible location. And tag bits are 2 bits, as we've shown over here. So for example, each block in memory has essentially a unique combination of tag and index bits. So this block, I highlighted the blocks that map to the same index for a good reason, because they're going to map to the same location in the cache, because we're going to index the cache, right? You can see that block 0, block 8, block 16. Did I do this right? Block 24, yes. 0, 8, 16, 24. They all map to, they all have index bits of 0, 0, 0. They all map to this location over here, essentially, in the tag store as well as the data store, because you index them in the same way. You can pick another one over here, block 1, block 17, block 25. What did I do? No, block 1, block 9, block 17, block 25. They all map to the same index bits, where the index bits are 0, 0, 1, right? Okay, you distinguish them based on the tag bits. Okay, so basically you access using the index bits. You get the tag store metadata out, valid and tag. You get the data out also. And then you compare the tag bits to the tag bits and also check the valid bits. If it's valid and the tag bit matches, you get a hit signal. And if it's a hit, the data is trustworthy and you can multiplex out the byte you're looking for if you're doing a byte access in this particular case, right? This multiplexer is to multiplex out the byte that you're looking for, but you get 8 bytes from the data store. Make sense? Okay. So basically, this is how it works. It's simple, basically. You know how to build all of this, actually, because you built register files, essentially indexing. But you have another comparator over here to make sure you're getting the data that you really are looking for. So, of course, the reason I highlighted these green things over here, the blocks over here, is these are the blocks with the same index. At least one set of blocks with the same index. These are the complete set of blocks that have an index of 0. The index bits are all 0. And these blocks contend for the same cache location. They can only map to this 000 entry in the tag store and 000 entry in the data store. And if they're accessed consecutively, they cause misses. So imagine an access pattern where you're accessing block 0 and block 8. Let's pick just those two. They cannot both be in the cache because they contend for the exact same location in the tag and data stores. What you will do is you will get a cache miss on block 0, place the block into the cache, and then the next access to block 8. You'll get a cache miss on block 8 because block 0 occupies that place. You place block 8 into the cache, and then you access block 0 again. You'll get a cache miss, and then place it into the cache. You access block 8 again, you'll get a cache miss. You place that into the cache. Basically, they're contending for the same location, and they're conflicting with each other in that same location. So that's not good, and that's the big disadvantage of a direct map cache. One block can go into only one possible location. If you have this bad access pattern where you have 2 blocks, or maybe 3 blocks, 4 blocks, 5 blocks, 6 blocks contending for the same location at the same time, you cannot fix the problem. So you need to have some more flexibility, basically. That's why we talked about flexibility early on. Direct map caches do not give you flexibility. Okay, I already said this basically. 2 blocks in memory that map to the same index in the cache cannot be present in the cache at the same time because one index has only one entry. And as a result, this can lead to 0% hit rate if more than one block is accessed in an interleaved manner, just like I showed you earlier, right? That map to the same index. So you can generalize this, right? Assume address A and B have the same index bits, but different tag bits. If you keep accessing A, B, A, B, A, B, A, B, A, B, A, B with that access pattern, they conflict in the cache index, and all access are conflict misses. Of course, if you manage your cache the way we discussed, right? If you manage your cache in a slightly different way, say, okay, I'm going to have some hysteresis. Let's say we're going to use the principle from branch prediction. Before evicting A, I want to see some other block to appear, let's say, multiple times. If you do that, then you get 50% hit rate on this access pattern, right? So with some smartness, with some carefulness, you can actually fix the 0% problem in some different way than what I'm going to discuss next. But the lack of flexibility still doesn't allow you a whole lot, right? Because this is a problem with 2 blocks. What if your access pattern is ABC, 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 ABC? What is it? ABCD, 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 ABCD. You're back to the square one almost, even if you do what I just said, basically. Okay, so that brings us to the set associativity, right? Addresses in this toy example, n and m plus 8 always conflict with each other in the direct map cache. And the idea is to enable blocks with the same index to have multiple locations to map to. Instead of having only one location, why not have multiple locations? Let's do 2 to begin with, more than 1. So you can also structurally think of it that way. Instead of having 1 column of 8, have 2 columns of 4 blocks. So if you look at the cache over here, you have a 1 column of 8 blocks, right? Tag and data store are both like logically equivalent to each other in the sense that they refer to the same block. But 1 column of 8, why not have 2 columns of 4? Meaning in each index, have some flexibility so that you can have 2 possible locations to place a block into. So this is how our tag and store and data store are going to look. This is what I mean by 2 columns of 4. Your tag store has 4 indices. So you have 2 index bits as a result, but each index has 2 possible locations. Data store is essentially the same. And we're going to call this a set. This is the set of locations that a particular block in memory can map to, depending on its index bits. And because we have 4 possible sets, we have 2 possible index bits. Now our tag became larger, as you saw, because we still have the same address size. So what you do here is you access the cache with an address, you get 2 tags and 2 val bits, and you get 2 data elements also, and you need to basically check, find the matching one. So you have 2 comparators. You have to compare to all of the possible blocks that you may have in the set the address that you're accessing. If there's a valid one and the tag of the valid one matches, then that's the one that you want to choose, right? Then that means that the block is in the cache. Okay. Basically, now you need to search within the set in an associative manner. That's why this is called set associativity, right? We not only index and do a tag match, we index and then do the tag match in an associative manner. You need to search all the tags and check all the valid bits, of course, and find if there is a valid one where the tag matches, that's the block you're looking for. Makes sense, right? So you've seen this actually. This is content addressable memory, right? We're really doing a content-based search. And it's going to be much worse, meaning more comparators when we do a fully associative. So of course, okay, you did the search, let's say. You also concurrently access the data store. You have 2-way set associative data store. So you get 2 8-byte chunks, 8-byte blocks. You need to decide whether any of them is what you want. And this logic over here says it's either this one or none. Because if it's not in the cache, then you fetch the data blocks, but that's not going to be what you're looking for. If it's in the cache, it could be this way or this way, basically. So that's the multiplexer to decide which block you're looking for, and then a byte in block to decide which byte you want to take out from the cache. Okay? So we made the cache a little bit more complicated with the set associativity, as you can see. But hopefully, now if your access pattern is AB, 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 they're both in the cache, and you still get 100% hit rate in the steady state. Ignore the filling of the cache at the beginning, right? So A can be here, B can be here, and they don't evict each other. Beautiful, right? Or block 0 and block 8 can be here. It can be accommodated in the same set. So the terminology is basically you index into a set, you have a set of blocks. In this particular case, you have 2-way associative, set associative. So you have 2 possible blocks in the set, and you do a content addressable search on the tags and also check the valid bits and find the way that matches. So now one more terminology. This is called way 0, this is called way 1. So you can match in one of the ways. So the key idea is really you have associative search or associative memory within the set that enables this. Now, the upside clearly, as I shown you, is accommodates conflicts better. Hopefully you get fewer conflict misses this way. That bad access pattern, AB, 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 went away. You still get 100% at the steady state. I'm ignoring the filling of the cache, hit rate in the cache. Downside is, clearly we made things more complex now, right? Because it's slower access, because if you compare to the earlier one, the direct map cache, this was nice. It was 1 comparator. Oh, sorry. This was 1 comparator. And there's no need for a mux in the data store. You don't access 2 things. This is the mux for the byte and block, if you will. Here, we have 2 comparators and a weight determination logic and a hit determination logic that became complex. And then the multiplexer, there's a multiplexer over here in the data store now. And then the byte and block multiplexer. So it's more work, basically. More hardware costs, slower access, larger tag store also. Don't forget, your tag store now you have 2 copies of the tag store. Each tag is larger, and you have a valid bit. Why is each tag larger? Assuming the same size memory, 8 blocks, we've organized in a different way. Instead of a single column, we have 2 columns, each of which is 4. So we reduce the index bits, but increase the tag bits, clearly. Okay, but this buys a lot of performance, actually, compared to a direct map cache. That's why a lot of caches today are set associated. Okay, in the old times, direct map caches were very nice because in the old times we didn't have a lot of transistors, right? This is where Moore's law helped us. Right now we have a lot of transistors. Transistor speeds are faster. As a result, people are able to build higher and higher associative caches. But this is still very fundamental, right? If you increase your associativity to be too high, your latencies and power also increase. I didn't talk about the power, but think about the power of accessing multiple structures concurrently. You drive 2 8-byte blocks out as opposed to 1 8-byte block out. So you're actually increasing the power consumption as well. Okay, 4-way, the same idea basically. Okay, what's the problem here? The problem is address n and n plus 8 always conflict. If you have address n, m plus 8, m plus 16, m plus 24, you're back to square one. And if you keep accessing them in that circular manner, this cannot accommodate. Even 3 of them, actually, this cannot accommodate. You'll get 0% hit rate again. So what do? You make it 4-way associative. So instead of 2 columns of 4 blocks each, have 4 columns of 2 blocks each. Meaning you have 2 indices, and each set contains 4 possible blocks. And your index bit becomes only 1, but your tag bit increases clearly to 4. So your tag store size increases again. But your likelihood of conflict misses become even lower. Now you can accommodate A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D nicely. Unfortunately, you get more tag comparators and wider data mux and larger tags, larger power consumption, etc. Now, larger power consumption is local, right? Globally, you may not be accessing the next level, so you may be saving power consumption, right? So always think about local versus global. Locally, your power consumption in this cache may increase, but because you're reducing the miss rate to the next level, maybe even memory, even power-hungry structures, you may actually be reducing the overall power consumption. So never forget the bigger picture, basically. The structure locally may consume more power, but that may be a good thing in the overall forest. Okay. Okay, now that brings us to fully associativity. So even this is a problem, right? What if you have A, B, C, D, E, A, B, C, D, A, B, C, D, E? Well, now that brings us to fully associative or fully flexible structure. A block can be placed in any cache location. And it looks like this, basically. There's no more index bits. There's no more indexing that you're doing. This is a completely content addressable memory. Earlier ones were partially content addressable. You're indexing, and within the set, you're doing content addressable set associative search. Here, there's no indexing, completely content addressable. You've eliminated the tag bits, index bits. So other than bytes and block, everything is a tag bit. So comparators, tag stores are very large. There are many comparators, and mux is very wide, as you can see. So today, people are able to build 32-way, 64-way associative caches, but they're not as easy, let's say. And the goal is to really reduce these conflict misses that we have discussed, right? And this is here you don't have any conflict misses. If you're managing your cache nicely, the key becomes managing your cache nicely, you should be able to get rid of all possible conflict misses. Of course, there may be a capacity miss, right? You really have 9 blocks and you cannot fit everything. Then you need to minimize your cache miss rate by managing things nicely. Okay, so basically what I've introduced is set associativity, right? And then we've also talked about the degree of associativity. If your degree is 1, that means direct map. If your degree is fully associative, that means if you have n number of cache blocks, any block in memory can be mapped to any of those n cache blocks. The question is how many blocks can map to the same index or set? Higher associativity, usually higher hit rate, but it's diminishing returns actually if you look at the curve. But it leads to slower cache access time. Both hit latency and data access latency actually increase. More expensive hardware, clearly. More comparators, larger muxes. And you get diminishing returns from higher associativity. So the picture looks like this. This is average across many workloads. It's not true for every single workload, of course, but as you increase associativity, the hit rate at some point starts kind of saturating. Average. Some workloads always keep benefiting. Some workloads don't benefit at all, right? Because of the access. It's very much dependent on the access pattern. Some workloads are perfectly happy with a direct map cache. You can construct those workloads, actually. Actually, I think that's going to be part of the homework that you have. Actually, nice homework questions where we give you the access pattern and you can reverse engineer the structure of the cache. If you know what you're doing, this is actually relatively easy. Okay. That's what people do, actually. A lot of security researchers do reverse engineering of hardware to understand, and software also, not just hardware, to understand what's going on. And those people actually know what they're doing in general. Okay, let's talk about issues in set associative caches. We're going to cover a lot of these issues in the next lecture. But there are a lot of issues, actually. I'm going to generalize things this way. So assume or think of each block as having a priority in the cache. And I think this is a very good way of treating how to manage a cache. You have different priorities for different blocks. And this priority indicates how important it is to keep the block inside the cache. You can also imagine extending this priority to other stuff that are not in the cache. Now, if you have a priority associated with all of the memory blocks at a given point in time, that also can guide you what to place into the cache. So this is actually a very powerful thinking. So the key issue is how do you determine or adjust the block priorities? And why do you want to do this? Because there are key decisions you need to make in a set, in a given set. In a direct map cache, this doesn't happen. Well, in a direct map cache, it can happen in the way that, do I evict the existing block and put in the new block, or do I not do that? That's the only decision you can make. Whereas in a set associative cache, you have a decision of eviction. What do I evict? I have two things. Which one do I evict to make room for the incoming block, assuming that I'm going to cache the incoming block? So these are called insertion, promotion, and eviction, replacement. Insertion means what happens to the priorities of the cache blocks that are inside the cache and the incoming block on a cache fill. You're filling the cache with a new block. How do you adjust the priorities? This is interesting because you can adjust the priorities in different ways potentially. The incoming block may be the highest priority potentially. If you're fully thinking that recently accessed blocks are going to be accessed are more likely to be accessed, more recently accessed blocks should have a higher priority, right? But that's not always true. So basically, insertion determines where to insert the incoming block, or even whether or not to insert the block. So based on the priorities, you decide that. Promotion means that what happens to priorities on a cache hit, meaning you access a block in a set, you get a cache hit. What do you do to the priorities? Do you increase the priority of the thing that you hit at that point? What happens to the priorities of the other blocks? Do you change them? Do you not change them? This is an interesting question, basically. Different policies take different decisions. Basically, whether and how to change the block priority. Eviction and replacement, what happens to priorities on a cache miss? You get a cache miss. Which block do you evict? Do you even evict any block? And how do you adjust the priorities of the blocks that are existing in the cache and the incoming one? Okay, so basically, this brings us to different policies. There are clearly insertion policies, promotion policies, and eviction and replacement policies. And these interact with each other, actually. It's good to take a holistic view and see that they're interacting with each other. And then we're going to talk about prefetching in one of the next lectures. That also interacts with all of these. So I think that holistic view is important. But we're going to look at them kind of separately to begin with so that we can reason about them a little bit. Right? So eviction replacement policy says, which block in the set do you replace on a cache miss? You have this block incoming. You missed in the cache. You couldn't find in the cache. So assume that we're going to put it into the cache, but we need to replace something because the cache doesn't have enough space for it. So clearly, if the cache has space, you replace that block. Meaning if there's something invalid in your cache, if there's an invalid block, you don't replace any other block. You basically put the block into that invalid location and make it valid. This makes sense, hopefully, right? Basically, you're filling the cache at this point. Right? If all blocks are valid, you consult the replacement policy. So replacement policy can be many different things, actually. You can randomly pick one block from a set. This may be okay, actually, if your access pattern is not predictable, for example, right? Or if your cache set is trashing, as we will see. Or there are many, many different policies that are proposed. First in, first out. If your access pattern is nice that way, maybe. Least recently used. This is something that many caches have employed, at least theoretically, they tried to employ. And the theory is that recently accessed data is going to be more valuable, meaning more likely to be reused soon. If your access pattern obeys that theory, then least recently used is a good replacement policy. And this is actually the temporal locality principle is about this least recently used. But it's not as strict, right? Least recently used is very strict, basically. You think about recency of use of every possible block and order them based on that. Maybe programs don't behave exactly like that. Not most recently used. So people try to actually approximate this least recently used, and you want to evict the not most recently used one, for example. There's some recency of use in the other ones. I know which one is not the most recently used, so I'm going to evict that one. So it's not exactly the same thing, but it's trying to approximate some similar notion. Least frequently used. So this is something different from recently, right? Frequently is how often did you need it, as opposed to when exactly you need it the last time, right? So these are actually different policies, and you need different metadata to keep track of this information. Complexity may be different also. Actually, it is different. So another idea here, least costly to refetch. Memory access may have different costs, actually. And there may be hybrid replacement policies. And then think about the optimal replacement policy. What's the optimal that you can do if you want to minimize the miss rate? What about if you want to maximize performance? Okay, so this is where I intended to stop, actually. We're going to start with some of these questions, and then we're going to look at many other different cache policies in the next lecture. I think next week we have only one lecture, right? Is it this Friday, right? Okay, then I will see you next Friday. Take care, have a nice weekend, and have a nice Thursday off.